We'll move on to the grafting density. Okay, so we have kind of defined this parameter in the last class. So this becomes important if you're going to have particles, okay, which have some long chain molecules that you have on the surface, right? And the grafting density, okay, you can call it a sigma g if you want to, okay, is defined as, what did we say? Number of grafted molecule per particle divided by surface area, right? In this case, if it is a spherical particle, is pi dp square. Okay, how do we get that? Some random thoughts as to how do we get this thing. See, one of the technique that people use in the literature is something like this. Okay, so typically when you take these particles that have these molecules, right? Okay, say that I have a silica particle SiO2, or I could have maybe a gold nanorod, okay, which again may have these things on the surface, right? What I can do is I can take a known quantity of the sample, okay, I can take a known quantity of the sample and then I can subject it to a heating process. Okay. Now, when you have silica particles or gold nanorods, we know that you can heat them to a fairly high temperature, they will not decompose. However, these long chain molecules that you have, it could be C18 chains, or it could be C12 chains or something like that. Okay. What will happen is, if you are heating a sample to a, what you do is you take a sample which has a known amount of particles and you start heating it. Okay. Now, when you start heating it at some characteristic temperature, all these grafted molecules can thermally decompose. Okay. Okay, what you do is, because you have particles of known mass, right, and then you can, this is typically there is a technique called TGA, right, thermogravimetric analysis, in which what you can do is you can take a sample, I can heat it at a controlled rate, controlled temperature. Okay. As you do that, what you do is you look for the change in the mass. Okay. So, these molecules start decomposing at a particular temperature and their decomposition ends at a particular temperature. Okay. Therefore, if you know the temperature range where they decompose and you basically estimate what is the change in the mass, okay, that occurs in that temperature window, I can actually get what is the total mass of all the grafted molecules that I have in the sample. Okay. If that is the total mass of the grafted chemical species that you have in the sample, if that is your MP, okay, or Mg, okay, that divided by the molecular weight of the grafted species, what will it give me? It will give me the number, so it will give me the moles, right, it will give me the moles of the grafted molecules that I have in the sample, that multiplied by Avogadro number will give you what is the number of molecules, okay, okay, number of molecules of the grafted molecules on all the particles that I have in the sample, right. I divide this by the number of particles that you have in the sample, okay. That will give me what is the number of grafted molecule per particle, right, and that divided by your surface area. If it is a spherical particle, it is pi dp square, that is what will give me sigma g, that is the grafting density. Okay. That is how it is typically done. There are other ways of doing it. Okay. In this simple TGA based analysis, what you do is you calculate what is the characteristic mass change that is associated with a particular chemical species that is either grafted onto the particle by a covalent bond or physically adsorbed, and you measure what is the mass corresponds to those species, that divided by the molecular weight, right, multiplied by Avogadro number will give me the total number of molecules that I have in the entire sample divided by the number of particles, okay, divided by your surface area will give you what is the grafting density. Okay. So, the next one that is specific that is surface charge density. Okay. So, before we do that, I have taken an MSDS, right. People who work with any chemicals, you would have heard this, right, MSDS, material safety data sheet, right. So, like for any chemical, there is also MSDS, or a data sheet for particles. Okay. And this is a typical data sheet. I have taken it from a website. Okay. So, if you look at this is actually for a PS, okay, polystyrene particles. Let us look at what all do they give. They give you the density of the particle, okay, 1055 kg per meter cube, refractive index. They give you a lot number. Okay. All the particles that you buy are kind of identified by this number. That means people can get this lot number, and then whether it is supplied here or elsewhere in the world, you will get particles of exactly identical nature, right. The mean diameter that is measured by TEM, okay, that is a standard deviation, right, something like this, which is obtained by, I said, right, you get this histogram, I can fit a distribution function, I can get the mean size and the standard deviation. There are other few parameters, you can think a little bit about it. I would like to highlight this quantity. Of course, they also show what is the specific surface area, right. I said for a spherical particles it is 6 divided by rho p into dp, right, you can get that, and this is the surface charge density, okay, 7.3 microcoulombs per centimeter square, right. I said that the surface charge density is defined as the total charge q, okay, on the particle surface divided by again the surface area, which for a spherical particle is pi dp square. Okay, that is how it is obtained. Okay. And there are other two nice parameters you can think about. Packing area per carboxyl group. Okay. So, if you look at the surface area is pi dp square, right, that will give you the total surface area. Okay. Now, if I divide that by the number of the charge group that I have on the surface, okay, this is an example of what is called as a carboxyl latex. That means it has carboxyl groups on the surface, okay, and if I know, so they also give you this quantity, right, carboxyl groups per particle. That means on the carboxyl, on the particle surface, there are 2.3 into 10 power 5 number of molecules, right, number of charge groups. Okay, therefore, this pi dp square divided by np, okay, number of this number of charge groups, okay, number of charge groups will give you this quantity, right, that is area per carboxyl group. Okay. So, all these parameters are important, if you really trying to do good set of experiments with your colloidal particles, you should worry about every physical and chemical properties of your particles. Okay. Only when you do that, okay, only when you have a complete characterization of your particles, thus when your experiments in terms of designing and in terms of interpreting the data that you get out of the experiments is becomes more meaningful, okay, when you have such a characterization like that. Okay. So, with that again we have already defined the surface charge density, okay, so C for charge, sigma for density, so which is defined as the Q there is a total charge that the on the particle surface divided by pi dp square, right. Now, there are different ways by which you can get q. We will talk a little bit about that this in detail a little bit later. At this point, I do not know how many of you have heard of a parameter called zeta potential. Have you heard this parameter, zeta potential? Okay. So, just to tell you in a simplistic term, if I may, so this zeta potential kind of tells you something about the charge of the particle. Okay. If the zeta potential is positive, okay, that means the particles are positively charged. Okay. If the zeta potential is negative, like here, right, they are negatively charged. Okay. And this is a unit of millivolts. Okay. We will learn that whenever you are working with charged particles in a fluid, it turns out that the mathematical treatment, okay, becomes much simpler if you not work with charge, but a quantity called surface potential. Okay. And again we will define what is surface potential in a while. Okay. So, this zeta potential can, for all practical purposes, can be taken as a surface potential, and okay, that is somehow related to q. Okay. Let us put it that this way at this point. Okay. Now, there are methods by which I can measure surface potential, okay, or the zeta potential, and from that there are ways by which I can get q, and once I have q I can get the charge density. Okay. So, typically this zeta potential is actually measured by a technique called electrokinetics. Okay. In which what you do is I have a dispersion of particles either positively charged or negatively charged, okay, and you apply a voltage, okay, and you make them move. Okay. Whenever you have a charged species, it does respond to the electric field that you apply, okay, and depending upon the velocity with which they move, okay, there are I can measure what is called the velocity with which the particles move, okay, and from that I can back calculate what is the charge in the particle. Okay, let us put it that way at this point. Okay. There are other methods of measuring it, not only electrokinetics. There are ways by which people do what is called a conductometric titration, okay, or potentiometric titrations, okay, in which what you do is you take a dispersion of particles and then you add a salt, okay, or an acid or a base, and then you measure the change in the conductivity or pH. Okay. And the way this conductivity and pH changes, okay, as a concentration of the electrolyte or the acid or a base changes, from that you can actually calculate the charge in the particle. Okay. And once you have that, I can actually calculate what is the surface charge density. The last parameter, surface heterogeneity, I have mentioned that there are two types of heterogeneity, right, a physical and a chemical heterogeneity. An example of a physical heterogeneity is particles that are rough. Okay. What you are looking at is a nice example where what has been done is they have taken 960 plus or minus 36 nanometer size particles, large particles. They are put into a solution which has 12, okay, 39, okay, or a mixture of 39 and 12, okay, and 72 plus 12. Okay. So, these are examples where I have a positively charged particles, I have a large positively charged particle, they are put into a solution which have negatively charged particles, okay, of different sizes. Okay. In one case only 12, second case a mixture of 39 and 12, a third case a mixture of 72 and 12, and because they are oppositely charged, these smaller particles are going to get deposited on the surface of larger particles, right, just because of the electrostatic interactions, and thereby they are able to get particles which have different roughness, right. In this case very small scale of roughness, in this case you have roughness of different degree, if you want to call it. Okay. Now once you have particles like this, I would have to characterize such particles also for roughness. Okay. So what people do is people typically use techniques such as surface profilometry, which is an interference based technique for measuring the heterogeneity on the surface, okay, or people can use AFM, atomic force microscopy, or any other technique, okay, and then what you get is what is called a roughness profile. Okay. This is as simple as if I have a surface like this, and if I draw a line, what I am going to have is I am going to have hills and valleys, right. They are going to be hills and valleys, okay, and you get what is called a line profile, okay, and then you kind of discretize it, and then you look at, you discretize into n equally spaced intervals, and then look at what is the height of the hills and the valleys. Okay. So therefore if you do that, and from this the height of the peak or the valley, I can get what is called a arithmetic mean roughness, okay, arithmetic mean roughness, which is simply 1 over n sigma of 1 to n, okay, the average, the size of this height or the valley, right, or you can get what is called a root mean square roughness, okay, by this simple formula, right. So therefore if we have particles that have physical roughness, okay, or a physical heterogeneity, one of the ways of quantifying such a thing would be measuring what is called the arithmetic roughness or a root mean square roughness. Okay. Similarly, we kind of roughly touched upon this point that there could also be what is called as a surface heterogeneity. What you are looking at is an example in this case where you have a particle which is homogeneously charged. Okay. What I mean by homogeneously charged is that we looked at that quantity, right, carboxyl groups per particle. Okay. Now what I can do is I can do a similar exercise, and I can go back and ask you a question as to, I have a particle whose surface area is pi dp square, right. I can take different regions, I am going to take a small section on the particle surface. I can ask a question as to what is the total number of carboxyl groups in that area. I go to a different location, I consider the same area again, and I can ask a question as to what is the number of carboxyl groups. Okay. If that number here and here or anywhere across the sample is exactly same, that will give you a surface which is chemically homogeneous. Okay. Of course, you could have cases where I could have a particle which is similarly charged, but I could have, if this is my average zeta potential, I could have minus 50 here, it could be minus 55 in some region or minus 40 in some region. Okay. That will still is an example of a case where I have a surface heterogeneity. That means there are pockets on the particle surface where the zeta potential is not same. Okay. Or you could have designed experiments where I could have a particle where some case, some regions the particles are positively charged, that may have positive zeta potential, and some region may have negative. Okay. That is again an example where this is an example of a particle what is called bipolar particles. That means these are particles which have both positive charges and negative charges on the particle surface. Okay. Or you could have cases where I have some region which is hydrophilic or hydrophobic, right. These are example of a surface heterogeneity, but chemical heterogeneity, and such things are more difficult to characterize. Okay. It involves more advanced techniques, for example, I was talking about this electrophoresis, right. You could have a case where I have a charged particle which may move in a particular direction when you apply an electric field. However, if you have particles which have heterogeneity like this, whereas patches where these things are positively charged, negatively charged, such particles could rotate in the electric field. Okay, you could exploit properties like that, and you can actually characterize the particles for chemical heterogeneity. Okay, but that is it involves more advanced techniques, more involved kind of work. So if you are interested to know a little bit more about this, you can read up some references that is here. Okay. Okay, with that I think we will end with the characterization of the particles. We will try and talk about a few other things in the next lecture. Okay.